This will be for physics, chapter 3, and this will be the second vector lesson. And it's going to focus on what are called components, or the pieces of a vector. Now, if you're lucky, and a vector is completely in the x direction, it only has one component, the x component, like here. So that is only x. If it's only in the y direction, you're lucky, it only has a y, and so you're set. When things get complicated is when a vector is like this one, and it's got a little bit of x and a little bit of y. What we are going to do is break them into their x and y components. So take this one right here, this vector. R, or the hypotenuse, is the vector. What I want to solve for is the y component and the x component and theta. So you have a choice here. You can either draw the triangle like I have here, in which I drew the vector, and then I said this is my x, and this is my y. But you can also do its matching triangle, and you can say that this is the x, and this is the y. Both of those will work. You just have to be careful that when you go to get your angle, like I mentioned in the prior lesson, please always do your angle from the positive x-axis counterclockwise unless we're told to do something different. Let's take a look at this example. A helicopter with very weird rotary blades is flying with a velocity of 75 kilometers per hour at a 35-degree angle to the ground. So to the ground in this case is following the pattern of counterclockwise from the x-axis. Now, this problem didn't give us any details about what direction it's flying other than the angle, but it didn't say north or east or anything like that. It really would have been helpful if it had. So let me just add that. Let's just say that it was flying east, which would match my drawing, or it might say in the positive x-axis, something like that. It didn't say, but we're going to go ahead with that. And if a problem doesn't tell you stuff like that, start your problem in your drawing as easy as possible. Don't add complexity unless you have to. So here's my 35 degrees, and here's my 75 kilometers per hour. If I draw that as a triangle, I end up with this. And so there are going to be two components. The y component here, notice, is opposite the angle. And the x component here is adjacent. So the equation we have for opposite, I have right here, hypotenuse times sine theta. And the equation we have for adjacent, I have right here, hypotenuse times cosine theta. So the hypotenuse is 75 in both cases. And then you do the trig function of the angle, and we end up getting 61 for the x, or horizontal, and 43 for the y, or vertical. And you can do a little bit of a sanity check here on these. If you look at our drawing at 35 degrees, it makes sense that the horizontal, or x value, or component, is bigger than the vertical, or y component, is a little bit smaller. You can kind of check your work on that. If you got these backwards, that means that you likely switched your equations right here between the opposite and adjacent angles, or excuse me, opposite or adjacent sides of the triangle. Here's a problem that adds a little complexity. So Dusty the camel is going to climb the Great Pyramid in Giza, Egypt, because that's what Dusty does. It's 136 meters high, 230 meters wide. Determine the magnitude and direction of Dusty's displacement. So in this case, what's happening is they're giving us the components and we're solving for the resultant. So we're going backwards from the prior example. In this case, this is where it really helps to draw it out first. If you don't draw it out, there's a good chance that you would go, oh, 136, that's my y component, and 230, that's my x component, and you would carry on and be wrong. But if you look at the picture, that 230, that is from edge to edge. And Dusty's not going from edge to edge, he's going to the top, which we assume is right smack in the middle between them. So that is why when I drew my triangle here, I cut the x component in half, but my y component is the same. We need to solve for r and theta. So our equation for r, the resultant, or the hypotenuse, is here. Plug in the values, and you end up with 178 meters. And again, that makes sense. If you look at the triangle, if this is 115, this is 136, we're solving for this one here. It's got to be more than 136, and so that makes sense at 178. For the angle, here's our equation, the inverse tangent, opposite over adjacent. So plug in the 136, that's the opposite. The 115, that's the adjacent, and you get 49.8, which means it's unlikely that a camel could actually do this because that's quite an angle, but Dusty's special. Next problem. A plane flies, I must have had words here in the past, 12 kilometers at 10 degrees. And again, if I don't say anything else, you assume that that 10 degrees is counterclockwise from the positive x-axis. And then it flies 8 kilometers at 120. What is the net displacement? In other words, it's asking what is the resultant vector. This one gets a little complicated, and it really helps if you break everything down and you label your work. If you're not careful, you might be doing the right thing, but you just get lost in the problem. So step one is to find the components of this vector and this vector. So I'm going to break these two vectors into their pieces. I have them drawn here. This is the first vector. I called it D1. And this is the second vector, D2. And I labeled this, notice 10 degrees from the positive x-axis and 120 also from the positive x-axis, because as you go over here, that would be about 90, and then I went a little more to get the 120. So if I redraw each of these as a triangle, I get this triangle here. And I did the math here. Since I labeled this D1, I decided to label its two component as D1x and D1y. And I solve for those the way that's been discussed earlier. Wouldn't be a bad idea to stop the video and practice. This triangle here, the second displacement, you have some options here. The way I've drawn the triangle, I decided to focus on this angle right here at 60 degrees. And I know that's 60 because I know that this from here to here is a total of 180. And if that other angle has gone 120, if you subtract 120 from 180, that's how I figured out that this remaining piece here was 60. And that gives me this triangle. So in this case, The adjacent is actually the x in this case, and the opposite is the y. So it matches the other situation. Now I prefer to do it this way. It makes more sense to me. So d2x and d2y. And if you use 60, it will give you a positive y component, and it will also give you a positive x. So if you use 60, you will get 4.0. And you just need to be aware, based on the drawing right here, this is a negative x component. And so based on that, you need to know to add the negative. Another way to do it would be to keep the original 120 if you prefer. And if you keep the original 120, you will still get a positive y, and it will give you a negative x. So it's your choice. I like doing it the way I have drawn here, but either way works for you. So check your work when you get to this point here. Check this and make sure that your positive and your negative makes sense. Then I've got my components. So here is my first xy components. Here's my second xy components. You add those together using simple addition, which I've done here. I called it d net x, d net y. That gave me these values. This is my x, this is my y. Now I just have to do what's called resolving them into the resultant vector. So to help me, I drew a picture of roughly what it would look like. So I did an x of 7.8, a y of 9.0. This is the theta in there in the middle that we want to solve for. Solve for the resultant magnitude, like we've done before. Solve for theta like we've done before. And you get 12 kilometers at 49 degrees. That makes sense because it matches my drawing here. And I recommend you do this drawing first. It also makes sense if I go back to the original situation, which was right here. If you take those two vectors and you roughly draw them, you get something like this vector, and then this vector. And then if you draw the resultant, you end up with this. And so you can think, does the answer in here make sense with what I've drawn right there in green? And it does, because I said 49 degrees, so okay, 49 degrees, that okay. I mean, I didn't draw it that carefully, but that works. And 12 kilometers, you can see my green arrow is a little bit bigger than both the red arrows. And so that means it's going to be similar, and that works out in this case. It ends up actually matching this one. That's just a weird coincidence. And that should do it for this lesson.